Okay, well let's move on to our final item of junk for today. And it's this thing. And in case you're thinking it's one of these high-powered amplifiers that people have in the Citroen Saxos, well, no, actually it's not. It's a mains inverter. And according to the data on it, I think it says on here somewhere, there we go, it's upside down. According to the information, it's a 1,000 watt continuous inverter with a 2,400 intermittent peak. And it was originally manufactured or supplied by Sterling Power Products, George Mill Street, Worcestershire, England. To be honest, I'm not holding up a lot of expectations regarding this actually functioning. I paid a grand total of £10 for this. Just picking this thing up, it feels suspiciously light. I mean, I know it's going to be some kind of switching regulator inside. In fact, many years ago, I actually used to work on some quite high-powered inverters that they used to install in boats and luxury yachts and things like that, made by an American company called Hart. And, you know, those things used to take 2 or 3 people to stag around with them. And there actually weren't much more than 1,000 watts. This is so-called claiming, but they used to have lots of copper inside and lots of transformer technology, and this is obviously some kind of switching technology, which I'm not quite so familiar with. Well, the chap that I bought it off said it did actually work, or he gave me those famous lines of, well, it was working last time I used it, which basically usually means it's broke. But I'm kind of guessing that probably like those Citroen Saxo amplifiers that people have with a boombox, I would have thought the most likely thing to have failed on it is probably some form of output transistor or switching transistor. So it should possibly be repairable. But let's not put the cart before the horse. Let's see if it actually functions. So yeah, it just doesn't feel really heavy enough. Maybe I bought an empty box. It just doesn't feel like there's much in it. And it would be interesting to see if it is actually capable of outputting 1,000 watts. I doubt that very much. I mean, I don't believe it for 1 second. So what have we got on the front of it? Well, we've got a few of these multi-standard fit nothing plugs on the front. It's got 2 of them AC output. It's got 3 LEDs. It's got a normal lamp, an over temperature lamp, and an overload lamp. It's got a switch which can be on. Top position is on, center position is off, bottom is remote, and there is one of those telephone sockets, like what you get on the back of a computer or modem. Can't remember what they call that. It's smaller than an Ethernet connector. Anyway, it's one of those small like telephone connectors. So I'm guessing that what this allows you to do is start or stop the inverter, well, remotely. On the other side of it, we've got a fan. We've got some nice EMC ferrets. Yeah, we've got two EMC ferrets here. Yeah, I'll have to be careful they don't bite me, won't I? So we've got the 2 EMC ferrets. What does it say on the back here? Warning: do not reverse input. Yeah, okay. It's obviously got a fan on it. Well, I guess the thing to do is plug it in and see if it does anything. Yeah, I'm not feeling 1,000 watts in this. Sorry, I'm just not. Well, this inverter's certainly going to need a lot of power to deliver its 1,000 watts, and I haven't got a power supply that's capable of delivering that. I suppose it's obviously designed to work off automotive batteries. So what we're going to use instead is we're going to use my TTI power supply, which is a little bit of a beast. I think it does quite happily. It does 20 amps at up to 20 volts. So we can quite happily supply 20 amps at 12 volts with this thing. Obviously nowhere near as much current as this thing will actually need to be running at full tilt, but we can have a go with it. Okay, so we've set that at 13 volts, and I've set the current limit to, well, 5.5 amps, 5.4 amps, because that's going to do to give us an idea, isn't it? Just to switch it on first, see if it does anything. I'm not holding out much hope. So we need one of them, one of them. Have I got it the right way around? Yeah. Good chance we're going to get these test leads smoking. Yeah, a bit of a difference there, but I think for test purposes we're gonna be fine. Well, it's obviously got a big capacitor inside it, so it's not drawing any current at the moment. Well, it is. It's drawing 0.1 amp. So there's nothing lit up. So I guess we just try and switch it on, and it does even switch on. I'm kind of thinking I'm somehow going to be a bit disappointed if this thing just works. Yeah, it sounds quite silly really, but I haven't really got anything I initially want to plug into this. I don't want to plug any of my fancy test gear into it just in case there is something wrong. I could actually do with just a lamp with a bulb in it, but yeah, they're a rarity these days, aren't they? That kind of thing. Let's try this thing. Is that doing anything? Well, it's lit up. Well, it says 231 volts. So, but interestingly, the current has gone up to 1 amp. So it kind of gives you an idea of how much current this thing must actually draw. So just the quiescent current of running this plug, it means I'm now drawing a supply current of 1 amp. Let me just let you have a look at that. So we'll just unplug this energy monitor. I dread to think how little power this... I just got a belt off that plug. That's great. Must have a capacitor inside it. Ow. But I always look at these inverters and, the idea of having this actually permanently wired or wired up to my car battery in a way that I can't easily switch it off. Yeah, no, just the thought of it fills me with dread. The potential fault current that you can draw from lead acid batteries. I mean, it's many hundreds of amps, and the thought of many hundreds of amps shorting out in my engine bay, no, horrible. So that's one of the problems with working on automotive stuff. We all do these stupid things. I mean, I bet all of us men of a certain age have been underneath a car, haven't we, with a spanner shorting out the starter motor solenoid after you've spent 5 minutes twatting it with a hammer. Somewhat of a rite of passage, isn't it? Okay, well, I've just been and found one of these lamps, and I'm going to put an ordinary light bulb in it. One of my precious possessions, this. Okay, let's just see which is on and off. That's on, off. Okay, so let's try it in the inverter. I'll just turn this lamp round a bit so it doesn't dazzle the camera too much. And 1, 2, 3. Surprisingly enough, it's working. On. You can actually hear a little bit of a whine from the inverter as it just copes with the load. Wonder what that bulb is. I don't know, it's not a very big bulb, that, is it? The lamp itself says 40 watts max. Probably is a 40 watt bulb. It's got nothing written on it. Yeah, it's certainly not a very big one. I mean, I've got a compact fluorescent lamp here. Let's see how it works for compact fluorescent. I'm sure it'll still drive that as well. Yeah, interestingly enough, the compact fluorescent only draws 2.1 amps from the power supply. Sorry, 2.7. Okay, so we'll just have a quick go with a compact fluorescent lamp. So that's drawing 2 amps. And we'll just change the compact fluorescent out for a normal lamp. And that draws a lot more current. Well, I've just unplugged this energy saving plug, and I picked it up when I unplugged it. I thought, oh, that feels really ridiculously hot, and just giving it a bit of a smell, it's got a really horrible smell of like burning plastic. I've got a feeling that maybe this plug uses a capacitive dropper power supply or something, and maybe I got a feeling, you know, the output from this inverter is going to be absolutely horrible. You know, not a sine wave at all. In fact, this is really quite hot, so I think that this inverter, I think, has done some damage to this. I mean, it still seems to be functioning, but yeah, it's got absolutely red hot. So yeah, maybe we'll have to have a look inside that later and see what's gone wrong. But a lot of these inverters, they're not true sine wave inverters. They kind of output some kind of horrible square wave, and if you actually power up something that's using you know, a capacitive dropper circuit in size, because of the very sharp rise time of the of the waveform, of the 50 hertz waveform, it kind of goes straight through the capacitors, and it, you know, the capacitors don't act as droppers anymore. You know, they're not resistive. I mean, I know they're not resistive anyway, but basically they let too much current through, because obviously the capacitors are designed to work at 50 hertz. Now the frequency is the same, but you know, it's not really the frequency, it's the rise time of the edges. Yeah, so I'm waffling now. You know what I'm talking about. So this smells as though it's just got very hot and not very happy. So I think what we need, I think the tool for the job is going to be Mr. Power Scope. So let's get Mr. Power Scope out and have a look. So basically, the output from this inverter isn't a nice sine wave. It's effectively a square wave. So this inverter's, you'd have to be very careful what you plugged into it, to be honest. Let's see what the response is when we switch the load on. Yeah, so the transient response seems okay. But basically any piece of equipment that uses a capacitive dropper isn't going to like this. I seem to remember quite a long time ago in my garage I used to have, I think it was an LED work lamp, one of these LED AND lamps that you use underneath the car. This is before everybody had batteries and stuff like that. And the house that I used to have, it used to have a garage, but it was remote from my house, so it didn't have mains electric. So I had a little mains inverter, and to be honest, it was quite good. I used to run the fluorescent tubes in the house. I used to run the fluorescent tubes in the garage, and you know, I actually managed to restore an MG in there without any mains power. It wasn't easy, but I managed it. Where there's a will, there's a way. But I remember I had this very cheap kind of LED hand lamp, and I remember just plugging it in and, you know, walking away from the bench and coming back 5 minutes later, and this thing was pretty much on fire. And it was because it was using a capacitive dropper, because I say what we really want here is we want a nice smooth sine wave, so that the rate of change of the voltage across the capacitor is relatively small. But you know, you can see the rate of change here. It's going, basically it does nothing and then it goes bah, and then it does nothing for a while, and it goes bah, and then it does nothing bah. So yeah, you got a very high dV dt, and yeah, so basically that's going to fire straight through a capacitive dropper, and it's going to toast anything on the opposite side of your circuit. And I suspect that's what's just been happening to our little power monitoring plug here. It, basically the power has just gone straight into this, and it's probably been frying some internal circuitry. So I don't know if it's permanently damaged or if it's, yeah, it's cooled down a bit now. But yeah, it makes me think, what am I going to do with this inverter? You know, it should come with a health warning. Please don't plug anything into me. I guess it'd be okay for running power tools. I think the guy that I bought it from, again, said he'd used it to start up his angle grinder. So I guess if it'll run an angle grinder, that could be pretty useful if you're outside or you need an electric drill. But I think you would have to be, you know, you'd have to be a little bit careful what you plug into this thing. And yeah, not sure what to do with it really. I'm not sure I'd even want to give it somebody. So it's obviously a very cheap inverter. If you actually see the better quality ones, the more expensive ones, they actually do produce a sine wave. It might be a step sine wave. It might still be made up of you know, little digital steps, but certainly you don't have this very high, this very sharp rise here. And I don't know if you can hear that, but the fan has just kicked on now on the inverter. So obviously the fan works on it as well. But it's kind of quite worrying. That is it warm? Well, it still feels pretty cool to the touch, which is a good sign. But one wonders, you know, if it's starting to get warm and require the fan when it's only got a desk lamp plugged into it, you know, a 40-watt bulb, that it makes you wonder exactly how hot this thing will get when it's outputting 1,000 watts. You know, I wish I had a big enough battery to try and test this thing. You know, plug a 1 bar electric fire in or something like that, see how long it lasts. But unfortunately, I don't have any batteries big enough to do that kind of test. But it would be interesting. Well, unfortunately, I can't really pull this apart, but you can see that we've got that green thing there. I can point my finger at it. That thing there. We've got this big capacitor, and that's in series with this resistor here. So I assume that's the thing that really was getting red hot before. And I've opened this up, and it's got that very pungent smell of impending electrical death. So I don't know whether or not we'll have done any permanent damage to this. Well, rather cheap plugging power energy monitor, but again, I think I've made my point here that yeah, got to be a little bit careful. Can't really open it up enough to get good enough access to see what's going on. I think everything's kind of well, everything's held down with hot snot glue, but yeah, it's definitely not a happy bunny. Well, I actually started making this video on this 230 volt mains inverter about 4 weeks ago, and I think some of you commented I haven't made any videos for a while. Well, just to let you know, everything's okay, no problems. Unfortunately, my dad had a little bit of a fall, so I haven't had a lot of time to make videos. I've been driving between kind of Sheffield and Manchester every night to go and see him in hospital. And he's out of hospital now and he's recovering. And I've also had a week's holiday myself, so been abroad. So unfortunately, just didn't have time to make any videos. Hopefully, with the onset of Christmas and a few days holiday, we'll be able to get a few more videos up. But yeah, no problems. Everything's okay. Now, for demonstration purposes, here's a little test circuit that I rigged up, and it's not particularly optimised. I just used basically the nearest components out of the junk box. So we've got a couple of LEDs. They happen to be white ones, and they're connected. 2 LEDs are connected in parallel. We've got a capacitor, which is acting as our reactive dropping element here. And then we've got another series resistor here, which is just a current limiting resistor. So I'll just sketch that out to make it completely obvious what we've got. There's our AC supply. So I was about to explain that basically we've got 2 LEDs here, and they're wired in parallel, but they're back to back. And we've got the capacitor, which is really going to be doing most of our limiting. Off the top of my head, this is what is it now? I think it's 100 nanofarads. 100 nanofarads, and if we do the maths of 100 nanofarads, 1/2 pi FC, plug all them numbers in, and I think we get something like 32 kilo. So we've got 32 kilo ohm, and that's in series with I don't know, a 700 ohm resistor. Don't get hung up on the values, it's not really too important, but basically the function, this capacitor here is the thing that's actually doing our current limiting. So yeah, we've got these two LEDs back to back. So on the positive half cycle, maybe let's, for example, this LED will conduct, but on the negative half cycle, if you didn't have this LED here, what you would find is there's no current being pulled through the circuit. So the voltage here would actually rise to quite a high point, and LEDs are quite easily damaged if you reverse bias them. Obviously the current will be limited when it's forward biased by, I don't know, the volt drop across the LED. I don't know what it is for a white LED, so I'm going to call it 3 volts. But when it's reverse biased, there is no current limiting in effect. Oh, sorry, there's no conduction. This LED won't conduct, so the voltage across it would rise. and yeah, that voltage would rise high enough to actually damage the LED. So just kind of a dirty trick is that basically you just put the LEDs back to back, and you'll find that if you could look at them in high speed, one of these LEDs will flash on the positive half of the cycle, and the other LED will flash on the negative half cycle. I'm not going to go into the calculations of how you work out these values. They weren't particularly optimized, literally, it's just what I had in the junk box in front of me. Okay, so let's have a quick look at our test setup. So we've had a look at our circuit here. This circuit is being fed with with mains power, which is actually being derived from my isolation transformer, which makes it a little bit safer. And I've also got this this variac, so we can just wind the voltage up. Because my voltage here at my house, it's actually quite high, and off the top of my head, it's often around 250 volts, or sometimes even higher. And what I wanted to do is have a similar voltage to what was coming out of that inverter. Now I'm going off memory again. I think when we were playing with that inverter previously, it was outputting about 230 volts. So what we'll do is we'll wind up the same voltage on the variac. We've also got the AVO meter here, which is set to the AC current range, and we've got the fluke meter here, which is just measuring the supply voltage to our test circuit. So let's just switch it on and wind the power up. So we're at about 100 volts, and we're drawing 3 milliamps for our LEDs. Keep going. 200 volts, 202 volts, we're drawing 6 milliamps. And we're just coming up to our test voltage now. Trying to get it fairly accurate. 230 volts. Well, I've just connected the power scope so we can have a look at the mains being supplied to our test circuit here. Let's switch on. And we've got what is a relatively nice sine wave here. And I'm guessing what I'm saying is a big difference between running the equipment off the variac, off the mains, is that the normal main cycle is a nice sine wave with a nice relatively slow rate of change. Whereas before we were going dum-de-dum-de-dum-de-dum, dum-de-dum-de-dum. So let's have a look at our voltage and currents. We've got our AVO meter here, and that's set up on the AC amps current range with 0.01 amps deflection, so sorry, maximum scale deflection, so that's 10 milliamps, isn't it? So we're actually drawing at the moment, or our test circuit is drawing, it looks as though it's about 6.6 milliamps. I'm not quite lined up with it, there's a bit of parallax error from where I'm standing. I'm going to go for 6.6 milliamps, and that's at 233 volts. So we've replaced the variac now with our inverter. Let's switch it on. LEDs have lit up, and back to our kind of horrible square wave with its you know, sharp rise times, which I'm kind of hoping is going to cause more current to be going through the circuit. And we are now drawing less current. Oh, about 1 milliamp less actually. We were drawing, I think it was 6.6 before, and now we're only drawing, well, it's about 5.6. It's hard to see because I've got some parallax error. Our voltage is approximately the same, 232 volts. So that didn't work, did it? My little test circuit here actually draws less current when it's being run from the inverter with its horrible square wave than it does when it's being fed with a normal sine wave. I wonder why. I'm sure you're going to leave it in the comments. The only thing I can think it could be down to is maybe, could it be something to do with the equivalent series resistance? Could it be the ESR? Because I think the ESR is basically an effect that comes on with frequency, isn't it? You need to use very low ESR capacitors in switch mode power supply circuits, and I think it's because the capacitors heat up if you don't. And that's certainly the effect that we were getting with this plug when we plugged it in. The capacitor was getting red hot. So is it ESR? Maybe it is, maybe it isn't. I'm sure somebody out there will know. So leave it in your comments. On that bombshell, I think we'll leave it. Thanks very much. See you again soon. Bye for now.